Section E4, Graphing Rational Functions. In this section, it's easy to remember four things when graphing rational functions. These are the four things that we've looked at already. The first thing to look for is asymptotes. So all types of asymptotes. So for example, horizontal, vertical, and slant. So those obviously involve end behavior. Look for holes, look for intercepts, and then some points on the curve if necessary. So if you need an acronym, I thought of AHIP, asymptote, hole, intercept, points. So let's take a look at examples 1 through 6, and our goal is to graph the following functions. So the first function here is m of x equals 2x over the quantity x squared minus 1. So we'll start by factoring to check for any discontinuities such as holes or vertical asymptotes, and we get those as a result of our denominator always. So we can see right away that the denominator factors into x plus 1, x minus 1. Now, since no factor repeats itself in the numerator and the denominator, then there's clearly no holes. But there are still two vertical asymptotes, one at x equals 1 and the other at x equals negative 1. Where do they come from? They come from these factors when set equal to 0. Because remember, whatever makes the denominator equal to 0 is a vertical asymptote or a hole. Next, we have to look at the end behavior to see if there's a horizontal or slant asymptote. And to do this, we look at the degree. Well, this is clearly a first degree, and this is clearly a second degree, because this power is a 1 up here, and this power is a 2. So our rule told us that if the numerator degree was less than the denominator degree, it's always going to be a horizontal asymptote given by the equation y equals 0, also known as the x-intercept. So again, so far we've got vertical asymptote, horizontal asymptote. Next, let's take a look at any intercepts. Again, there's no holes in the graph, so you don't have to worry about it. Next, we look at the intercepts. To find the y-intercept, there's always set x equal to 0. And if we do that, though, this time, we're going to get 0 over negative 1, which is just 0 as a result. So this is my y-intercept here. Well, if 0, comma 0 is a y-intercept, then it's also an x-intercept. But let's go ahead and prove that. To find the x-intercepts, we go ahead and set the y value equal to 0. So put a 0 in here, and we end up with this equation right here. Well, what we'll notice is that for this to be 0, obviously only the numerator could be 0. The denominator we can multiply up to get rid of it if we like, since there's no repeating factors in the numerator and denominator for any holes. So as a result, we just get this 2x equals 0 right here. And if 2x equals 0, it means that x equals 0. So our x-intercept in this problem is the same coordinate as our y-intercept, because they're just the origin in this case. Now let's take a look at the graph of this. Okay, we're going to use points in a minute, but what can we already plot is the question. We can plot a vertical asymptote here and here. We can plot a horizontal asymptote, and we can plot an x and y-intercept, which is really on the same location. So let's take a look at what that means. So far, we take a look on the right over here, and we'll see we have everything listed. Here's our vertical asymptote at x equals 1, our vertical asymptote at x equals negative 1, the horizontal asymptote of y equals 0, and the intercept of 0, comma 0. Now it's clearly obvious that we need points, and the way to do this is as follows. Use your vertical asymptotes or your discontinuities as boundaries. So pick numbers bigger than 1, pick numbers less than negative 1, and then pick numbers in between here. So these numbers here, negative 3, negative 2, negative 1.5, these are numbers out here. Then we look at values right here from negative 0.75 to 0.75. Those are x-coordinates in here somewhere. And then we go from 1.5, 2 to 3. Well, 1.5, 2, and 3. So we're going to see all these data points here. Okay, all the data points in the table, and it makes it a lot easier to connect. Now, without the asymptotes, one might think that the graph looks, like something like this. Who knows? They might think it looks like this. Right? I mean, that's clearly not a function, but without the asymptotes, you don't know that you shouldn't connect these dots, and that the function is clearly discontinuous. But, again, if we didn't have those asymptotes, you might try to connect them and think of this as a continuous function, but it is clearly not a continuous function. So this is indeed not the curve. So as a result, though, once we plot all those points, we plot the points on the graph, and we can see clearly here when you have these 3 points, and this is an asymptote, and this is an asymptote, it's got to curl in this region here. Well, up here, here's an asymptote, here's an asymptote, so this curls here. And then finally, this asymptote here and this asymptote here, at first it's like, alright, well, we have to be between them, but we can cross over a horizontal asymptote. And we can clearly see that it crosses over because this is the x-intercept. Example 2 says, graph the function x squared minus 9 over the quantity 2x squared plus 1. So as always, we start by factoring. We factor the numerator, and that's pretty easy. We clearly can see that there's no holes right away, because if we think about this, there's no repeated factor in the top and the bottom. Then remember, to find any vertical asymptotes, we set the denominator equal to 0, or factor it and set it equal to 0, although you can't really factor this. So just simply set this equal to 0 to find vertical asymptotes. Now, here's the thing. When we set this equal to 0, we're going to see that this moves over and it becomes imaginary. Okay? The result of this equation is imaginary. The solution will be imaginary. So there are no vertical asymptotes in this problem. Now the question becomes the horizontal asymptote next. Well, when the degrees are equal, we can see this is squared and this is squared. We look at the ratio of the leading coefficients. So there's a 1 here and there's a 2 here. So it's just simply 1/2. So y equals 1/2 is the horizontal asymptote. Next, to find the y-intercept, remember we set x equal to 0, and we could really just look at the ratio of the constants, which is -9 over 1, or simply -9. So our y-intercept turns out to be 0, -9. Our x-intercepts, we have to remember to set the numerator equal to 0, provided there's no holes, so nothing cancels. So setting the numerator equal to 0, we get 3 and -3 as our x-intercepts. So clearly all we have are intercepts. I'm sorry, and we also have a horizontal asymptote. But we don't have any vertical asymptotes or holes. So we might want to plot some points to help us. Because if we just simply graph what we've got, right? If we just graph the horizontal asymptote, that's right here, the dashed red line. The y-intercept is down here, and the x-intercepts are out here and out here. Well, that's clearly not enough. Maybe this is a V, maybe this is some sort of a curve, maybe this line connects like some piecewise function. So we graph these points, or we plot these points, and we'll just pick points in here and in here for the x-coordinates, so we're going to see our values. And when plotting these points, it's a little bit more obvious the kind of shape this graph will obtain. Example 3, graph g of x equals x squared plus 4x minus 5 all over the quantity x minus 2. So again, we start by factoring. There's no holes because there's no repeated factors anywhere. There's a vertical asymptote at x equals 2, because that comes about when we set the denominator equal to 0, giving us x equals 2 as our vertical asymptote. Next, since the degree of the numerator is greater than the degree of the denominator, we can see that's a 2 and this degree is a 1. We have a slant asymptote, so we use synthetic division or long division. Okay, so we take the numerator, 1, 4, -5, that goes along the top. This x minus 2 comes out as a positive 2. Bring down the 1. 2 times 1 is 2, plus 4 is 6. 2 times 6 is 12. 12 minus 5 is 7. Remembering that this is what we get as a result. Since this started with x squared, this becomes x plus 6, and then plus the remainder. Remember that the remainder does not matter because we're looking at end behavior as x goes to infinity. So as x goes to infinity, it makes this denominator infinity. 7 over infinity is just really 0. So this last part doesn't really affect the problem. So x plus 6 is our slant asymptote. Next, we want the y-intercept. To find that, remember, just look at the ratio of the leading, or of the constants. Right? That comes about by setting x equal to 0. So again, these three would all drop off, here, here, and here, giving us -5 over -2, or 2.5, and that would be the y-intercept. Now to find the x-intercept, remember to set the numerators factors, these two equal to 0, giving us -5 from the first one, and +1 from the second one, so these are my x-intercepts. So again, start by thinking of what the graph would look like so far. Again, this is what we have. We see that we have a vertical asymptote at x equals 2. That's right here. We've got a slant asymptote, the line y equals x plus 6. We've got our x-intercepts at -5 and 1, and our 1 y-intercept at +2.5. Now, we have to pick points clearly, because it looks like we're going to be somewhere in this region here, and then maybe out here, out here, out here, but we're going to be outside of our boundaries. So let's pick points in here somewhere, and then also out here. Now in doing so, as a result, we get these values. So I pick points like -6, -4, -3, -2, -1 to give us more points in here to see that we're just connecting a little smooth curve. And out here we pick points like 3, 4, 5, 6, 7. So this is x is 3, x is 4, x is 5, x is 6, x is 7. And we'll see that we have this symmetric curve. Okay, this curve that exhibits symmetry known as a hyperbola. So in example 4, we're looking at a rational function that has a quadratic over a quadratic. So we start by factoring. And what we notice right away is that x plus 7 is in both the top and bottom. So it's gone really, and there's a hole now at x equals negative 7. Well, how do we find the location of that hole? We take a look at the simplified form right here and plug in the value of x that makes it a hole. Well, negative 7 does. So we do h of negative 7. And if we plug that in, we get negative 11 over negative 9, which is 1.22. So that means that the hole, its coordinate, is negative 7 from the x value earlier, comma 1.22. Now, if these are gone, we look at the simplified form just to find the vertical asymptote, and x equals 2 gives us a vertical asymptote here, and that's this value right here. Next, we can say since the denominator degree and numerator degree are the same, there's a horizontal asymptote that's equal to y equals the ratio of the leading coefficients. In this case, is 1 over 1. So 1 over 1 is just 1, so y equals 1 is the horizontal asymptote. After that, we can look at the y-intercept and set x to 0, or simply, again, look at the ratio of the constants in this case. Negative 28 over negative 14 is just 2, so in this case, the y-intercept is 0, comma 2. And then finally, to find the x-intercepts, we have to remember that x plus 7 is already a whole, so only the x minus 4 up here helps cause this to be an intercept. So we set x minus 4 equal to 0, giving us x equals 4, or 4, comma 0. Now again, we'll make a mental sketch over here, but we'll notice right away that the x-intercept, the y-intercept, the hole, the horizontal asymptote, and the vertical asymptote are not enough to graph. So we're going to pick points. Remember, let's pick points somewhere in here, and we'll pick points very close to the vertical asymptote to see this curl. And the same thing goes down here. We'll pick points very close to the vertical asymptote. So for our x values, we choose numbers such as negative 4 for x, negative 2, then we choose 1, then we choose 1.5 for x, and on the other side we're going to choose 2.5, 3, and then 5 for x. And we'll see all of our y values here corresponding to the graph on the right. So we can clearly see that this hole is on the curve, but the curve clearly is continuous, 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 continuous. Discontinuity, it jumps over the hole, and then it continues. So we have a discontinuity here, and we have a vertical asymptote as a discontinuity in this problem. Example 5, we're looking at the function u of x equals the quantity x squared plus x minus 12 all over x plus 4. Now this one's really interesting, because there's tons of applications in science where a function is linear, but it has a discontinuity somewhere in it. In this example, you're going to clearly see that actually, and I recommend you look at a graphing calculator. And if you just graph this in your calculator, this is what you're going to see right here, which looks like a line, which doesn't make much sense. But the reason it's a line is because, take a look, we've clearly got a hole at x equals negative 4 because of the repeated factor. There's the hole at x equals negative 4. So remember, we take a look at the simplified form here, and we plug in the negative 4. In for x. So if we take u and plug in negative 4, do u of negative 4, it becomes this here, negative 4 minus 3, which is going to be negative 7. So the hole's location is negative 4, comma negative 7. And that's this you're going to see right here, negative 4, comma negative 7. And then after that, we can just pause and think about the graph of a line on our calculator. The real thing we're going to be graphing is just simply this, u of x equals x minus 3. Okay, so we're simply going to be graphing this line right here with the hole at the coordinate negative 4, comma negative 7. And we can clearly see that the intercept is going to be at positive 3. Right? When we set this equal to 0, we get an x-intercept of positive 3. Well, that's right here on the graph at the x-intercept. The y-intercept, if we set x to 0, we get negative 12 over 4, which is negative 3, and that's the y-intercept right there. But I don't even need to do the intercepts here, because once I cancel these factors from the hole, now all I've got left is a linear function. Now, example 6, we have a linear function over a quadratic function, and we're going to start by factoring the denominator, and we can see right away that there's no hole in this case because there's no repeated factor, right? The numerator is x minus 4, the denominator doesn't have x minus 4 in it. But clearly we have two vertical asymptotes. If we set x equal to 0, the denominator becomes 0. If we set x equal to 3, the denominator becomes 0. So 3 and 0 are the vertical asymptotes. Okay, now x equals 0 is really just the y-axis. So already you're going to see there's a vertical asymptote on the y-axis. And the other one is over here at x equals 3. Since the degree of the numerator is less than that of the denominator, the horizontal asymptote is always going to be y equals 0, and that's this red dashed horizontal line. Finally, we go to the y and x intercepts. Well, the y-intercept, if you plug 0 in for x, you get negative 4 over 0, which means it does not exist. And this makes sense since the y-axis is a vertical asymptote. If this is a vertical asymptote right here, there can't be an intercept on it because it's a point of discontinuity. To find the x-intercepts, we just set the numerator equal to 0 as always, giving us x equals 4, or 4 comma 0 as the x-intercept, and that's right here. So this is clearly not enough to graph, so we go ahead and we pick points. And notice what I'm doing. I'm picking points to the left of here, so in this region, pick points in this region, and then pick points in this region. Always use your vertical asymptotes as boundaries for your points. So in this region, we're using these first 4 points right here to graph. In the middle region right here, we're using these 4 points. And then on the right side, we're using the points 3.5 and 5. Okay, plotting all the xy coordinates as ordered pairs, we're going to see the curvature of this graph. Now notice, the horizontal asymptote of y equals 0 on this side acts normally. And over here, we're going to see this just comes down and acts normally with that asymptote. But here, the function crosses the horizontal asymptote, and then it actually comes back toward it over time, and it will run alongside of it. Finally, example 7 says make your own rational function that has the following characteristics. It crosses the x-axis at 2 and 4. Okay, so right away, think graphically. At x equals 2 and x equals 4, there's going to be x-intercepts there. There's a hole at x equals negative 1. I don't know what the height of the hole is, but I know somewhere at x equals negative 1, right? Somewhere along this x equals negative 1 location, there's a hole, maybe here, maybe here, maybe here, here, somewhere. There are 2 vertical asymptotes, one at x equals negative 5, so that's back here somewhere, and the other at x equals 6, maybe all the way out here somewhere. And then finally, there's one horizontal asymptote, the line y equals 3, so that's like this here. So we've got a lot going on. So what we're going to do is we're going to see that we can come up with many different solutions for this, okay? But there are certain things that need to be true. So let's start with some random function r of x. And since it has x-intercepts at 2 and 4, that means that the numerator has to have x minus 2 and x minus 4. Automatically. It's got to be there. Now since there's a hole at negative 1, it means that x plus 1 must be in the numerator and the denominator. Remember this, x plus 1 in the top and bottom would give you a hole at x equals negative 1. And remember that the x minus 2 and x minus 4 is what gives you the roots, or the x-intercepts. If there's a vertical asymptote at negative 5 and 6, it means that we need to have x plus 5 and x minus 6 in the denominator to get a vertical asymptote. So already we kind of have a rational function right here. But the last part says that there's a horizontal asymptote and it's y equals 3. Well, clearly we're going to see that this is going to be cubic and this would be cubic, right? Because there's 3 different factors on the top and the bottom. So if it's a cubic over a cubic, to get a horizontal asymptote, remember it's the ratio of the leading coefficients. So it's whatever the leading coefficient up is here, so it could be like 9 over 3, or it could be 6 over 2, or it could be 3 over 1. It really doesn't matter at this point, it can be anything. So what I'm going to do is, I'm going to say to myself, well, let me just put a 3 up here, and a 1 down here. Okay? Now, as a result, I'm going to have to think about what I've got. If I were to FOIL these out, or multiply them out, I get that numerator, and FOILing out the bottom, I get this denominator, but clearly I want a 3 up top, so I need to distribute the 3 to everything, so triple all of these values up top. This becomes 3x cubed, this becomes a negative 15, this becomes 6, and this becomes 24. So now the leading coefficients ratios are 3 to 1. Okay, 3 over 1. And let's take a look finally what that graph would look like. The graph of this function right here looks like this on a calculator, and we can see all the characteristics. Here's the vertical asymptote at negative 5, and here's the one at positive 6. Here's the x-intercepts at 2 and 4. Here's the hole right down here. Here is the horizontal asymptote at y equals 3.